So to go ahead, I welcome Abhay Chauthaji, sir. He's a graduate from COEP. He did also a PG diploma in material management. He has 38 years of experience with Bharat Forge, Bajaj Auto, and SKF. He was a core member of value engineering projects. He did a lot of value engineering projects, development of titanium forgings, aluminum forgings, control cooling cycles for microalloyed steels. He reduced the heat treatment distortion for crankshaft and front axle beams. Also, he did a lot of failure analysis and troubleshooting. Abhayji, we would love to listen to failure analysis. One more lecture from you on this. So just keep in mind and oblige her, sir. Also, he was a part of. He is actually a core member of new part development, new process development, new product development during his tenure in Bharat Forge. So today we will hear from him about the forging and heat treatment of forgings. So over to Abhayji,
Yeah,
and everybody, all the participants, please be on mute. And whatever your questions are, please put it in your chat box. We will definitely answer all these questions after our session, a technical lecture is over. So over to Abhayji.
thank you, sir. I'm just sharing my presentation. 1 minute. Just a minute. I'm sharing it. Can you read this?
Yes, we can see it.
Yeah. Now I will start my today's presentation. The topic for the presentation is practical approach in forging process and heat treatment of forging. Basically, when we say the forging, what is the definition of the forging? Forging is defined as metal working process by which metals and alloys are plastically deformed to the desired shapes by the application of compressive forces. Basically, the raw material is heated in the dies and it acquires the shape of the impression of the die. When it is around 1250, 1260 is the temperature normally follow the carbon steel forgings. Now in forging, there are two types of forging which are well known. One is open die forging and the second one is closed die or impression die forging. When we say open die forging, it is performed between flat dies. There is no impression die in the open die forging and there are no pre-cut profiles in the dies. It is a plain flat die which is used in the open die forging. And larger parts, normally 10 ton and above, and the length which are very long, like 80 feet, 90 feet, which are normally cannot be forged in the closed die operation, those are forged in the open die process. Normally it is used for the components which are small in quantity. Where the quantity is small, those are not worthwhile for going for a die preparation because it is very costly affair. So for small quantity and the sections are very big, those are selected for the open die forging. And like the size is very big, for sugar industry or for cement industry, very big shafts are required. Those are generally open forged. Now coming to the impression die forging, uh, impression die forging presses metal between two dies. One is called a top die, one is called a bottom die, and that is nothing but the tooling, and that contain a pre-cut profile of the desired part. So normally if it is a crankshaft or it is a connecting rod or whatever the component is there is a pre-cut profile in the die impression, and when hot metal is kept in that impression and then the dies, the top die comes in contact with the bottom die, and by force the material gets filled in the that impression area. So that is the normal process for the closed die. So impression die forging and how the operation takes place. In impression die forging, two dies are brought together and the workpiece undergoes plastic deformation until its enlarged sides touch the side walls of the die. Then a small amount of material begins to flow outside the die impression. That is nothing but the flash, the excess material of the raw material that is coming in form of the flash, and the other material gets fed in the die impression. This flash cools rapidly and presents increased resistance to the deformation, and that helps build up pressure inside the bulk of the workpiece that aids material flow into the unfilled impression. So if the pressure is not sufficient, there are chances that the job can be underfilled. So the right section of the material, right weight of the material that is selected to have the good forging. Now coming back to impression forging, there are different steps that are normally being followed, like process flow diagram, then raw material, that is for any forging it is required. Then there are varieties of types of forging and their processes. Then the heat treatment, their properties, then certain testing of the forgings are involved, and we see some forging defect. So one by one we will go details for that. So this is a general process flow diagram for any forging. Initial is the raw material, that is, it is receipt and inspection. So any forging is to be made, we have to get the material from the steel mill. And then there is some inspection plan is there based on the confidence with the steel mill and based on the criticality of the component, some percentage of the material that gets inspected and then material is cleared for the forging. Once it is cleared, then there is a operation called as the billet cutting. So normally it is cut on the saws, and somewhere it is manual operation, somewhere it is auto operation. Once it is cut on the cutting machine, then the next operation is the forging. Then after forging, there is an inspection during forging operation that is called as hot inspection or green inspection. That is when the initial die is set and some forgings are made. That time the in charge over there, he checks the component which are made initially. That is dimensionally, whether the dimensions are okay, whether the surface quality is okay, whether scale is not there. So all those visual inspections part, those are done at this stage. It is called as hot inspection. Once the hot inspection is over, then the bulk production starts and the jobs are forged over there. Then the next operation is heat treatment. Now there are certain grades of material, those require heat treatment, but there are certain grades of material that don't require heat treatment. They are called as the microalloy steel. So by virtue of the chemistry of the material and by virtue of controlling the forging process, the desired properties and desired hardness, those are achieved. So I will explain that process in detail in the subsequent slide. But the jobs where the heat treatment is involved, though after doing the heat treatment, then the next operation is shot blasting. Now, as you are aware, this material which being used, that is a steel. So at the raw material stage, as well as at the forging stage and at the heat treatment stage, every time the thermal treatment is there. So during heating, there is a lot of scale on the component. So the remove the scale, the operation which is used is shot blasting. So there are varieties of shot blasting. The thumb blast is there, or round table blast is there. So based on the component size, normally these blasting machines are selected. Once the job is cleaned by blasting, then the next operation is dimensional inspection as well as metallurgical inspection. Once the material passes through this or the component passes through this, then the very important inspection stage, or that is called as the crack detection. Now this crack can be there on the component either because of the raw material defect, or it could be because of the forging process, or it could be because of the heat treatment process. So there is a very stringent requirement for checking the crack on the component, and by chance if the crack is not properly detected, then it is likelihood that it can go to the customer and it may result in failure. So this is very important stage for crack detection. And once the jobs are okay in this inspection area, then the final operation, that is oiling and packing. So this is a general process flow diagram for any forging. Now, when we say forging of steel, Then the raw material is the first thing, that is the type of the steel, grade of the steel, chemical composition, and content of the specification. So normally raw material, those are either plain carbon steel, that is where the carbon is in the range of 0.2 to 0.55%, or those could be alloy steels. That is in addition to carbon, there are certain additions like chromium or molybdenum or nickel in certain percentages, or vanadium. And apart from this, there is a grade called as a microalloy steel grade. It is having very small additions of vanadium and titanium with some percentage of nitrogen. So again, what is that microalloy steel and where it is used, that I will explain you in the subsequent slide. Now, when we get the raw material, based on our customer's requirement, though there are different standards are used, like ASTM or BS, that is British standard, or DIN, that is a German standard, JIS, this, that is a Japanese standard, EN again, that is a British standard, and GHOST, that is a Russian standard. So as per the customer requirement, these various standards, those are being adopted. Now we have to see why these different alloying elements are there and what is the effect of that alloying elements. Now when manganese is added, the manganese contributes to the strength and hardness dependent upon the carbon content, and increasing the manganese content decreases the ductility basically, and also it decreases the weldability. Manganese has got a significant effect on the hardenability of the steel. So whenever somebody wants to have the higher hardenability material, manganese is the best alloying element to get that property. Then the phosphorus, that increases the strength and hardness, and it decreases the ductility and much impacts toughness of the steel. The adverse effect on ductility and toughness are greater in quench and tempered higher carbon steel. So that is the reason normally for a good quality steel or good clean steel, the phosphorus percentage is always kept as low as possible. Because normally if phosphorus percentage is higher, then that also affects the fatigue life of the component. Then coming to sulfur, sulfur decreases the ductility and notch impact toughness. But the advantage of the sulfur is it improves the machinability. So sulfur is found primarily in the form of sulfide inclusion. And because of the sulfide inclusion, if they are properly distributed, those help for proper machinability. Then silicon is added, that is as one of the principal deoxidizer, and that is used in the steel making. Silicon is less effective than manganese in increasing azimuth strength and hardness. In low carbon steel, silicon is generally detrimental to surface quality. So normally silicon in the forging, that is in the range of 0.15 to 0.30, that is the normal specified range. Then the copper in significant amounts is detrimental to hot working steel. Copper can be detrimental to surface quality. So again, that is the reason normally for all forging quality steel, the copper is kept as low as possible. And normally it is 0.2% max. Then the most again important alloying element which can enhance the property, that is a nickel, that is a ferrite strengthener. And nickel does not form carbides in the steel. It remains in the solution in ferrite, strengthening and toughening the ferrite phase. Nickel increases the hardenability and impact strength. The basic advantage of nickel, wherever the high impact property requirement is there, in that case nickel is added. And molybdenum, that increases the hardenability of the steel and it enhances the creep strength of the low alloy steel at elevated temperature. So these are the general alloying elements which are added in the steel for getting the various properties. Now I am showing one slide where the grades which are being used normally in abundance in the forge shop, like 1045M, it is a medium carbon steel, or 4130, SA 4130, it is carbon plus chromium steel. 709M40, this is as per base standard, it is again carbon and chromium steel, and moly steel, it has got moly also. Then 20M05, it is a case carburizing grade where carbon percentage is low, but it has got manganese and chromium as the alloying elements. Then 42CrMO4, which is very widely used in majority of the forge shops for various components. It has got chrome and moly as the alloying element with carbon 0.38 to 0.45. Then EN9, it is again medium carbon steel. H55C, again medium carbon steel. H48C, again that is a plain carbon steel. So these are the major uh, varieties of the steel which are used abundantly in the forging applications. Now, when we want to get the material, we have to give the specification to the steel mill for getting that right material. So what are the contents of that specification that one need to know? The first thing is the chemical composition. For any grade, one should know what exactly chemistry we are looking for. Then cleanliness level, that is the inclusion rating. Normally sulfide, alumina, silicate and uh, sulfide, alumina and silicate and uh, those are the different inclusions which are present in the steel, and there is a cleanliness level acceptance norms are there. Those are followed to accept the steel. Then coming to the grain size, normally HTM 5 to 8 is the grain size which is adopted for acceptance of the raw material. Then the hardenability, again, there is a GIS standard, GIS HTM255 for acceptance of the hardenability norm, and that is nothing but the depth of the hardness. So that is again one important criteria. Then the microstructure, that is when we get the raw material, we have to cut the section to see that there are no subsurface crack or center crack in that cut section. So that is called as the micro analysis. Then the ultrasonic soundness, that is the internal soundness of the material. That when we get normally bigger sections, then one has to be sure that internally the material is defect free, crack free. So that is checked by the ultrasonic method. Then the reduction ratio. This is again one more important criteria. When we get the raw material, at the raw material stage, the reduction from ingot to the roll bar or from bloom to the roll bar, that is calculated. And normally there is a specification given by the end user. Either they want 4 to 1 or 5 to 1 or 8 to 1, depending upon the final application. So this reduction plays very important role for getting the basic internal soundness of the material actually. Higher the reduction ratio, better is the soundness. Then coming to the root of the material, that is melting and casting, whether it is a continuous cast material acceptable or only ingot route is required, because for certain application like big crankshaft and some critical application, some customer they prefer only ingot route. So this route is also very important for selection of the process actually. Then the hardness. When we get the rolled billet, then normally hardness should be 300 or 290 BHN, which helps for better cutting of the material. If the hardness is high, like for alloy steel, like chrome moly nickel grade like 321 BHN, then it poses some problem for cutting. So normally steel mill has to take care like slow cooling or something, that process has to be adopted to reduce down the hardness. Then the next criteria is decarburization, which is the depletion of the carbon near the surface. If it is very high, it is not acceptable. So there are certain stringent requirements from the customer, like application like connecting rod or front axle beam. Customer demands very less decarb. So to have that less decarb at the raw material stage, the decarb has to be very low. So that is again important criteria for accepting the material. And then the surface quality. Here comes the size, and size can be either round or RCS. When we, for any forging, based on the designer's actually this thing selection criteria, either material can be round material or round corner square. It is not perfect square. So what is the reason for RCS? That the material flow is better when it is round corner, and the tendency for cracking is less. If the round corner square is not there, then there are chances that material will get folded in the forging, and the flow of the material also will be poor. So normally the material is either round or RCS, and it should be free from any seams or any crack or any rolling mark. So by chance any of these defects are there on the rolled billet, the same can occur on the forging, and then it becomes very tedious job to remove those defects. Now coming back to forging, the process of metal working either in hot or cold condition to desired shape. That is what the forging we have just understood. So we have to now see different type of forging, then their process layout, equipments, and forging process, and what typical components in the forging normally those are made. So as we have seen earlier, it is open die forging and closed die forging. So this is one open die forging press, and there you can see heated very big ingot. Already some pre-shape already is there, and this is uh, Z press is there where this open die forging is going on, and this is a closed die forging Weingarten press, which is a German make press is there where closed die forging takes place. So these are some examples which are shown over here. So again, when we go for forging process layout, the first thing is billet cutting. Then normally the forging temperature range is in the range of 1250 to 1280 degrees centigrade. Then it is subjected for forging. Depending upon the component configuration, there could be different stages like either blocker or finisher or maybe extrusion or maybe upsetter. So that will vary based on the final component configuration. Once the forging is done, then that whatever the flash gets generated, that has to be trimmed off. So there is a trimming operation is there. After trimming, there is little bit bending on the component which has to be padded to get it straight. So it is a padding operation is there. Then there is a inspection for dimensional. Then crack detection, that is for magnetic particle inspection is there on sample basis. And then it goes for the heat treatment. So this is a general process layout again for any forging. So this is forging again can be on hammer, which is an old way of forging, and where a lot of manual involvements are there. A lot of people are required over there. There is very less automation when hammer forging is there. Against to that, when we say a press forging, so there is a lot of automation is there. So if you say the manpower required for press against the hammer, so very less people are required when the forging is done on the press, as well as since the controls are very, very good on the press, the input weight of the material is less compared to the input weight for the hammer. So that is the advantage. Plus because of the automation, the output, production output on the press is very good. So when the quantities are in large number, those jobs are normally processed on the press. Now these are some forgings like this, like connecting rod. This is one crankshaft. This is a front axle beam. This is a steering knuckle. So we can make varieties of forging, and based on the size of the forging, different capacities of the presses or hammers, those are selected. So what are the requirements in the forging? The dimensions should be as per the drawing. Then forging has to be crack free. It should be free from surface defect like scale pit, nick mark, and the flow to have directional property. The basic advantage in the forging, you get the directional property. So here there are some examples like this is one hub is there, which is sectioned and then it is cut, then it is polished and ground, and then it is etched. So after doing the etching, you see some flow lines over there. So the material flow takes place as per the contour of the die cavity. So this is one cut section of the crankshaft. This is a pin, this is a journal, and you can see this flow over here. So this is the grain flow, which is as per the contour of the component. And normally when the machining takes place, then it should not cut over here, because if the grains are cutting at certain angle over here, then that area becomes weak, where during the service the failure chances are occur. So the designer has to design the die very properly so that the material flow is very safe inside the die cavity, and there is no material flowing outside the die cavity. Similar the case for the connecting rod. In connecting rod, again the material is the grain flow is seen over here, which is along the contour of the die cavity. Again, the requirement over in the connecting rod, the grain should not cut sharply on these sides, because this is the area where in the service the maximum stress comes on the job. So by chance any grains cutting over here at sharp angle, then that area becomes very weak, and there are chances that it can fail in that area. So the grain flow plays very important role, and the designer has to design his die to take care of the proper grain flow. Then once the forging is done, we are coming to the heat treatment part of it, where we have to see the different classification of the heat treatment, various equipments those are used for the heat treatment, types of the quenchant those are used, and the requirements of the heat treatment. So this is just I'm briefly explaining. This is a hardening process where this is time and temperature, where the material is heated to certain temperature, hold for certain time, then it is cooled at certain rate, that is quenching. Again, it is loaded for tempering for a temperature in the range of maybe 500 to 700 degrees centigrade. It is unloaded, put in air. So this is normally process called as the hardening and tempering. This is a normalizing operation where again material is heated to certain temperature, maybe around 850 to 900, 920 degrees centigrade. Then based on the section thickness, it is hold for certain time in the furnace. It is unloaded and air cooled. This is called as normalizing operation. Then the isothermal annealing for certain application like gear or shaft for paste carbonizing grades. Normally this isoannealing process is followed where again material is heated in a furnace, normally 930 to 940 degrees centigrade. It is hold for certain amount of time, maybe 1.5 hours to 2 hours. Then it is cooled around 650 to 680 degrees centigrade. Again hold there for certain amount of time, 2 hours, 3 hours. Then it is unloaded and air cooled. So basically this process is gives the basic ferritic palladic microstructure which helps for better machinability. And then the stress relieving. Here after heat treatment is done, like crankshaft or front axle beam, when the jobs are straightened, then after straightening, lot of stresses getting incurred on the job. So we need to relieve those stresses. Those stresses are normally relieved by the process called as stress relieved, and the temperature that is normally used, that is 30 to 50 degrees less than the tempering temperature. So again, it is loaded in the tempering temperature around 480 to say 600 degrees centigrade, hold sufficiently for 2.5 to 3 hours based on the again section thickness of the component, unloaded and air cooled. So this is a stress relieving operation. So post this process, there are certain components which require post machining some heat treatments like induction hardening or carburizing or nitriding. So when we carry out this heat treatment, there are varieties of the furnaces in the heat treatment shop, like bogie furnace, where the capacity can be 1 ton up to maybe 8 to 10 tons for single bogie charging. Then the batch furnace, it is again a batch operation. There they can be again from 500 kg to 2 tons, 3 tons like that. Then a continuous furnace. It is a continuous operation, 1 in, 1 out operation, where capacities can be 1 ton per hour, 2 ton per hour, 3 ton per hour like that, based on the requirement. Then there are furnaces called as steel quench furnace, which are having the control atmosphere. So why control atmosphere is required? Because for certain jobs, when they are processed in the machine condition, then there is no scale formation over there because of the control atmosphere, as well as no distortion. So that is the advantage of the steel quench furnace, normally followed for the machine component. And one more operation called as a fluid bed furnace, fluidized bed furnace, which is again for critical component where no distortion is expected. There the fluidized bed furnace is used. Now, for operation of these furnaces, there are different fuels are normally used, like light diesel oil (LDO), then liquid petroleum gas (LPG), or electricity. So these are the general fuels which are widely used in majority of the heat treatment shops. The quenchants which are used for the heat treatment, basically either it is oil, or it is polymer, or it is water, or it is water based, that is one salt is there which is mixed in the water. So the selection of the quenchant, that depends upon basically the grade of the material as well as the configuration of the component and the properties which are required for that component. So based on these three requirement, either we can select oil quenching, or we can select polymer quenching, or water quenching, or salt based quenching. So what are the advantage or heat treatment, or what for it is basically done? Basically to improvements in the properties to have the better fatigue life. When we are doing the heat treatment, the fatigue life gets enhanced. You get basically the required hardness, then the mechanical properties such as tensile and impact test, then the microstructure as maybe ferritic perlitic or maybe benitic or martensitic based on the again requirement on the component. uh, these structures can be achieved by following the desired heat treatment. Then the forging has to be crack free, because there is no point after doing all this process if the crack is there on the component, then the total process will go waste, and the defective jobs should not be sent to for further processing. So it has to be crack free, for which a test called as MPI or magnetic particle inspection that is carried out. And then the straightness and dimensional control, that is again very important. If the job is bent or the dimension is not okay, that is not again acceptable. So for carrying out this test, there are certain ASTM standards are there. For tensile test, ASTM A370 is normally referred. Again, for impact test, ASTM A370 is referred. For hardness, ASTM E10 is referred. And after carrying out the different processes and conducting tests, then randomly some jobs are cut for distributive test for microstructure analysis. So that microstructure, if it is ferritic perlitic, this is normally structure. You can see this white, that is a ferrite, and the black water is seen, that is a perlitic structure. Then this is structure called as the benitic structure, and this is some tempered martensite structure with some little bit partial decarb near the surface. So these are varieties of structures based on again final requirement. Those can be achieved. Then Minoflux, there is a normally MPI inspection is there in every shop, and as a thumb rule, generally 800 amperes per inch current is applied for checking the magnetic particle inspection, and then straightness as per the drawing, that test is carried out. So when we do all these testings, there are certain or all these forgings, there are certain defects those can occur on the forging during the forging process. The first one is lap. That is nothing but the fold. When the job is getting forged, some material during the hammering operation that gets folded in the form of lap, and then that is shown as a crack on the job. And when it is cut, then that crack can be deep also, and that can scrap the job. So very proper care has to be taken during forging process to avoid such type of defects. Then the cold shut, where the lubrication is applied during forging in the deep dies. If the lubrication is not proper, in such areas some cold shut defect can occur. Then some crack, if it is on the raw material, that can further get appear on the component also. So that has to be removed. Then binding, that is if the raw material binding is there because of the chemistry or the steel making, that defect we have to see. Then the underfill, if the die is not properly filled for some reason, then the dimension is not as per the drawing requirement, the job has to be scrapped. So this defect is also not acceptable. Then the mismatch, if the die is not properly set, either front or side way mismatch can be there, and the dimension again will not meet the drawing requirement, and we have to scrap the job. Then neck mark defect, it is in the when the jobs are very hot and after forming is made, then those are required to be kept on the tote box or on the pallets. So while transferring the job in the hot condition, those are not properly handled. Then in the hot condition, there could be some marks coming on the component, and if that mark is very deep, that again job gets scrapped. That is called as a neck mark. Then the scale pit. During forging again, whatever the scale formation is there, normally that is getting blown off by blower over there. Normally on the top die, that scale blowing takes place successfully and efficiently, but in the bottom die sometimes very difficult to remove the scale, and that gets trapped over there, and that gets adhered to the component. And if that is very thick and it gets embedded in the component, then the surface of the component becomes very rough, and that normally it is not acceptable. The crocodile skin is the surface which is irreparable or irreversible, and the job has to be scrapped. Normally, it happens when the forging temperature is out of control. That is, normally you want to forge at 1250, and for some reasons there is some failure on the furnace controls, and temperature goes maybe around 1380 or 1400. Then this type of defect can occur, and there is no way of repairing it. We have to scrap the job. And then the hold up, that is basically the dimension as per the drawing. So these are the general defects which occur on the forging. So what are the advantages of the forging? You get directional properties, you get good combination of strength and toughness, then consistent dimensional control is there, because in the same die we are consistently getting the output, so the dimension control is very good. Then the yield is very good in case of forging. What the meaning of yield is, suppose initially you are using a component of 100 kg raw material, and the component weight is 80 kg. So in that case, it is 80% yield. So in case of forging, the yield is very good. Then the complicated shapes can be manufactured. This is again advantage of the forging process. And the higher life of the component. Because of the forging process, you get the directional advantage, that properties in the directionality, and because of that, the fatigue life of the component is very good. So these are the various advantages of the forging. Once this forging part is over, now I will little bit explain regarding the heat treatment in more details. So for the heat treatment, there are bulk treatments called as annealing, normalizing, hardening, and tempering. And there are certain case and surface hardening treatments are also there, like carburizing, nitriding, carbonitriding, which is chemical diffusion base, or induction hardening, flame hardening, laser hardening, which is thermal diffusion base. So these are the thermal treatment, either bulk or surface treatment. And when thermal treatment is there, for example, heat and quench, that is coming under the thermal treatment. The mechanical treatment is short pinning. When certain component like front axle beam or connecting rod, those are short pinned for getting the better fatigue life, because you get better compressive stresses on the component. So that is advantage of doing the short pinning. And there are certain chemical treatments are there. So either those can be a combination of thermomechanical or thermochemical. So heat treatment, either it is a bulk or it is surface related. When we say bulk, it is either annealing or normalizing or hardening and tempering. If it is a surface, then it is thermal or thermochemical. Just I explain you, either it is maybe flame or induction or laser like that. Or for thermochemical, it will be carburizing or nitriding or carbonitriding. In case of annealing, there are again, either it will be full annealing or recrystallized annealing or stress relief annealing or spheroidized annealing. So what are these annealing? We can just explain based on this diagram. Here it is a percentage carbon versus the temperature, and this is a part of iron carbon diagram, where for full annealing and hardening process and normalizing process, it has to be above A3 over here. For the carbon up to 0.8%, and for the carbon above 0.8%, for normalizing, normally the temperature is above ACM temperature. And for full annealing and hardening, it is normally above A1. So this is the temperature range of 727, which is for A1, and for A3, it starts from 910 degrees centigrade till it reaches to 727. So when we say full annealing, the purpose of this heat treatment is to obtain a material with high ductility. A microstructure with coarse perlite, that is perlite having high interlamellar spacing, is endowed and such properties. The range of temperatures used is given in the figure below. You can see again, just I explained you, it is shown over here. The steel is heated above A3 temperature for hypoeutectile steel. The steel which is up to 0.8%, that is called as hypoeutectile. So it is heated above A3, this red marked line, and it is heated above A1, that is This is the A1 for hyper-eutectile steel. And then steel is furnace cooled to obtain the coarse perlite. Then coarse perlite, it has got the low hardness, but the ductility is high. Because the hardness is low, naturally the ductility is very good. For hyper-eutectile steel, the heating is not done above ACM. Heating is not done above ACM to avoid the continuous network of the pre-eutectile cementite along porous grain boundaries. So normally it is avoided to heat above the ACM temperature for full annealing. For recrystallized annealing, again, if we refer to the same diagram, uh, during the any cold working operation, say cold rolling, the material becomes harder due to the work hardening, but it loses its ductility. This implies that to continue deformation, the material needs to be recrystallized. That is, wherein the strain-free grains replace the cold work grains. So this recrystallization annealing is used as an intermediate step that is in cold deformation processing. To achieve this, sample is heated below A1 temperature. It is heated below A1 temperature and it is held there for sufficient time for recrystallization to be completed. Then coming to the stress relieving operation, due to the various process like quenching and different cooling surface, surface as well as in the interior of the component, phase transformation like martensitic or transformation, welding, etc. The residual stress develop in the sample, and to relieve those stresses, the stress relieving operation is carried out. And this is periodized annealing again. So like stress relieving, this treatment is done just below A1 temperature. And this is normalizing. Again, normalizing, as I explained you, for the hyper-eutectile steels, normalizing is done 50 degrees centigrade above the annealing temperature. And here, this is the normalizing over this red line, it is shown over here. And then the hardening. The process same like normalizing, but subsequently it is cooled fast in any of the quenchant based on again the final requirement. Either it will be oil quenched or water quenched to get the martensitic transformation basically. And this is through hardening, that is from surface to core, how the hardness variation takes place, that is explained in this particular graph. So for Jomini hardenability, normally the sample is 4 inch long by 1 inch diameter is there, and that is cooled from the bottom. So it is quenched from this side. So rapid cooling from this side, and the top side is slow air cool. And then the hardness is checked after polishing grinding, and then the hardness is checked, that is called as the hardenability band. And the variation of the hardness along the Jomini bar, that is then calculated. So this is basically hardening, and then the tempering operation is done again to get the desired property, desired hardness. So this is the way heat treatment is done, hardening and tempering. So who are using this heat treatment? Like aircraft industries, they are using, automobile manufacturing, they are using, defense sector, for shops, foundry shops, heavy machinery divisions, then manufacturing shops, powder metal industry. So heat treatment is required for so many different industries. Now, apart from those grades where the heat treatment is done, there are certain grades where no heat treatment is required. So this is called as microalloy steel or air cooled ferrite perlitic steel, that is AFP steel. It is air control cooled ferritic perlitic steel. So for the AFP steels, those steels which possess reasonably high tensile strength in the range of 750 to 1100 MPa megapascal and yield strength 450 to 700 with a microstructure predominantly ferrite and perlite with no or small amount of uniformly dispersed precipitates of vanadium or titanium, those resulting from cooling the forging in air. That is, by virtue of the proper cooling in the forging, we get vanadium carbonated precipitation, which gives the proper strength and proper microstructure to the component. And the alloys which are being used, those are normally vanadium and titanium in very small percentage. Normally vanadium is 0.2% max and titanium with 0.03% max. So these are the basic alloying elements which are added in the microalloy steels. So for what automotive component this can be used? Like crankshaft, it can be used for connecting rod, for front axle beam, for camshaft, for steering knuckles also, for control arms, and for the axle tube. So there are varieties of the application where this uh, microalloy steel can be used. So which steels have been replaced by AFP steels? Like steels like 42 CRMO4, that is chrome moly grade, 41 CR4, that is only chromium steel, EN24, that is chrome nickel moly grade, EN19, again chrome moly grade, which are quench and temper grades. Those can be replaced by using the microalloy steel grades. So normally when we compare the properties of quench temper versus microalloy steel, in quench temper, these are the general requirement for tensile strength. It is 800 to 1100 ultimate tensile strength. In microalloy steel, you get roughly almost same property, 750 to 1100. So there is very marginal low compared to quench and temper. Similar the case of yield strength. In quench and temper, normally you get better yield strength, like 500 to 800, as compared to microalloy steel. It is a little bit low. It is 450 to 700. So where the high yield strengths are required, there one has to go for the quench and temper. Then elongation, again there is drop in elongation as well as area reduction for AP steel, and the major drop is in the impact. For quench and temper process, you get better impact in the range of 35 to 100 joules, whereas for AFP steel, the impact properties are very low. Those are maybe 10 to 40, it is mentioned over here, but most of the time you are getting in the range of 10 to 20 only. So is lower impact strength not a concern? So why, in spite of using micro steel, there is no problem for impact strength? So there are certain theoretical backup for that. When we say there is no concern for impact, the reason is notched impact strength as measured by conventional uh, CHARPY or AZ test is only of very limited value as a criteria for design. Then this is because the test methods and not geometry are considered exaggerated and unrealistic. Then advances in fracture toughness studies confirm this point. And the practical example is the development of fracture split connecting rod, where the C78-6 material is used. Its splittability simply means a very low impact strength. So in spite of having the low impact strength, it is used for the connecting rod application. The basic difference in the conventional material and the microalloy steel, for the conventional material, the process is die forging, then again it is hardening, then again it is tempering, then sometimes technique is involved, then relieve the stresses, stress relieving is involved. So it is a very lengthy process for the conventional forging and heat treatment. Against that, when we are using microalloy steel, it is only forging, then control cooling. So by virtue of the chemistry of the material, as well as the virtue of the control cooling process, you get the desired properties, desired microstructure. So that is the advantage of the microalloy steel. So what are the advantages? So uniformity in the microstructure, that is phyletic structure, and hardness, as well as quenching and tempering process is very sensitive to section size. Variation of the hardness normally in quench and temper job you see, but in case of microalloy steel, that variation is very low. What are the advantages of AFP? Again, for quench and temper, the greatest technological advantage is the absence of distortion or cracking in the entire thermal cycle of the control cooling process. Because since there is no quenching process, there is no thermal cracking over there. Then because of that, there is no distortion. Since there is no distortion, there is no straightening, no SR. So that is the advantage. And since scaling and distortion is minimal, can afford to have reduced machining allowance. That is one more advantage of using the microalloy steel. Plus, it has got the better machinability because normally microalloy steel, the sulfur levels are high. Because of that, the machinability is better. And for crankshaft application, when we use microalloy steel, then by NDT method, we can check the case depth very easily. So that is again one more advantage. This is just, for example, I am showing some equipments which are used like Brinell hardness testing machine. This is a Rockwell hardness testing machine. This is a dual purpose micro hardness test unit for Vickers and for Noop hardness. This is Vickers micro hardness indenter head and microscope lens. This is optical metallurgical microscope. This is a cutting machine. This is metallurgy sample preparation, abrasive cotton machine. And this is scanning electron microscopy for further detailed analysis of the failure sample or fracture analysis. This is for creep and stress rupture testing machine, where we have to check this test. There are testing machines available like creep and stress rupture test. And this is rotating bending fatigue test rig for conducting the rotating bending test of fatigue. And these are normal samples for fatigue test, like this shape. And I will go through just few slides for various microstructures which normally we get in the forging industry. This is normally untempered martensitic structure, where you can get this martensitic needle shape over here at 500 magnification. This is tempered martensitic structure, again at 500 magnification, but those needle shape, those are getting broken. You get a tempered martensitic structure over here. This is when the quenching is not so effective, you get some Benedict structure. So instead of martensite, which is tough for machining actually. This is partial decarb of around 0.7 mm over here. So this is a ferritic polytic structure, and here the more loss of carbon is seen, that is the decarb layer. So this is called as a partial decarb over here. This is one microstructure perlitic with grain boundary ferrite. So these boundaries, grain boundaries are, those are the ferritic grain boundaries, and this is the perlitic structure. And this is at 100 magnification. The same structure when we see at 500, here you can see in more magnified form actually. Then this is microstructure at 100 magnification. It is again, you see grain size 4 to 5, some microalloy steel microstructure where we are getting ASTM 4 to 5. And if the process is not controlled and temperature is very high, there are chances that you can get very coarse grain, here ASTM 0 to 1. So if we get such type of coarse grain, that is not acceptable, and that component is then rejected. That means the control in the forging is not good. This is again structure where uniform ferritic polytic structure is there. This is at 100 magnification. This is at 500 magnification. These are certain microstructures like retain austenite or fine tempered martensite with surface Benedict structure over here. This is fine tempered martensite structure. So there are various samples in of different cut sections. Now this is a typical microstructure. After machining crankshaft, certain defects are seen over here. So to understand what the defect is there is a grinding burn test is conducted. You can see the surface, it is retempered defect over here, retempered burn, here rehardened burn. So the whatever the gray shade is there, that is seen different over here. So this rehardened burn depth, wherever it is there the hardness is very high, 58 HRC, 55 HRC. And this is the retempered burn where the hardness is around 241 micron depth is there, the hardness is less over here. This is again one structure of gases, nitrocarbureous case depth. Here you can see a white case over here, and at 100 magnification, the same sample at 200 it is seen over here, and that case depth also can be measured under microscope. This is a quench crack sample where first sample is unetched, and the same sample after etching is seen over here. You are not seeing any decarb near this crack. So this is a quench crack. And this is a forging defect decarb surrounding the crack. So this crack is seen, and adjacent to the crack, you are seeing these white areas. That is nothing but the decarb. that implies that this defect has occurred in the forging process. And this is again one defect. This raw material defect decarburation surrounding the crack. This, you can see the defect is having some angle. It is not straight. So during the rolling process, that defect has acquired this angle. So one can conclude that this defect has occurred in the rolling process. So this is in short. I have covered what is the material, what is the forging process, what are the different heat treatment processes, and what are the uh, remedies for that. Hello, Mr. Urian. Hello.
Yeah, good evening. Sandeep would be taking up the questions which have come in our chat.
Yeah.
So thank you very much. It was absolutely stunning lecture.
It was little bit fast because the area which I wanted to cover was little bit more.
Yeah, but
Orion screen.
it was. I cannot imagine. You know, सरस्वती नुसती वाणीतनं वाहत होती एवढ्या चांगल्या रीतीने तुम्ही घेतलं ते व्हेरी नाईस व्हेरी नाईस इम्प्रेस्ड आणि वी हॅड लॉट ऑफ पार्टिसिपंट्स दिस टाइम I think we clocked 93 this time. Actually, I did not do much of marketing this time because we had meetings and 5:30, 6:30. So after 6:30 we started doing marketing and we clocked almost 93. So just short of few shorts of 100. But it seems that these lectures are becoming very, very popular amongst all our heat treatment fraternity. And it was very nice that you explained it in such a good this thing that anybody who has not worked in forging area could visualize everything, and it was very nice. In fact, Santosh had told me that he is a very nice orator, but it was so nice. You are so nice orator. I could see for the first time. Thank you very much, sir, for coming and enlightening us on forgings. There are a few questions which people have asked. So let me go through them. Is there any advanced method developed to check structure and grain flow without destruction? So that's what the question is from Amit Madhav.
Structure and grain flow.
So if you can take.
Without.
Structure and grain flow without destruction.
Unfortunately, it is we cannot unless we destroy the job, because for checking the grain flow, one has to cut the section in the longitudinal direction, and then we have to cut it, then polish it, grind it, and then etch it. So that is a destructive method only. Non-destructively, it cannot be checked.
Is isothermal annealing whether it gives strength similar to normalizing, and does isothermal annealing give good hardness control? That's one of the questions.
Isothermal annealing is little bit long cycle compared to normalizing. In the normalizing, we are having only cycle of high temperature, that is 850 to 880 or 900 degrees centigrade, and just plain air cool. But in case of isothermal annealing, we are holding at high temperature, again cooling down to 650 to 680, again holding there for certain time, then unloading and air cool. So normally the cycle of isothermal annealing is roughly 7 to 8 hours as compared to 3 to 4 hours of tempering, normalizing. So the best structure in isothermal annealing is better than in normalizing. You get uniform ferritic perlitic structure in case of isothermal annealing. In normalizing also you get ferritic perlitic structure, but the hardness in isothermal annealing is lower than the normalizing.
There is another question is hardenability test. If you could elaborate, test data on please elaborate on hardenability test data interpretation.
This hardenability, Jomini hardenability is nothing but the depth of hardness. So normally, as per HTM 8255, based on the different alloying elements in the steel like carbon, manganese, chrome, nickel, moly, vanadium, that hardenability factor that gets enhanced. And normally for carbon steel, if it is a plain carbon steel, the hardenability when we convert to the ideal critical diameter value, it is in the range of 1.6 to 1.9 inches. Normally for alloy steel, it is chromium steel, it is in the range of 3.5 to 4.0 inches. If it is chrome moly steel, then it is in the range of 5 to 6 inches. So the ideal critical diameter is nothing but the hardenability, and the definition of the ideal critical diameter or DI value, when you quench that section, at the core you get 50% martensite. So the hardenability gives the depth of the hardness basically, and by converting it to the ideal critical diameter, the metallurgist can control the incoming material for getting the better properties on the component. So it is very important actually property for getting the depth of the hardness.
So there's another question, which is most apt forging method for hollow shafts in the range of 2 to 4 kgs, if you could elaborate.
Hollow shaft can be either extrusion process will be there. Normally there are presses available where extrusion process is followed for making the hollow component, and that is the one which is normally being used largely actually.
Yeah. So can you explain depth, case depth checking with NDT?
Yeah. Now in case of crankshaft like from microalloy steel, it is if it is a 38 mm waste foil material, and when crankshaft is made out of that material, the basic structure is ferrite and perlite. When that ferritic perlitic structure crankshaft that is induction hardened, then that case around 3 to 4 mm, suppose that is the case required. So up to the depth of 3 to 4 mm, you get martensitic structure. So the surface of the crankshaft on pin or journal, that is martensitic structure up to depth of 4 mm, and below that the structure is ferritic perlitic. So by non-destructive method, by because of the differential microstructure, it can give the different value during ultrasound waves are passed in the component, and you get that because of different structure, you get the exact value where the cutoff is there, and based on that, whether the depth is 2 mm or 3 mm or 5 mm, that exact case depth can be measured. So that is the advantage of for microalloy steel. For basic regular conventional steel like chrome moly or carbon steel, it is very difficult to differentiate surface microstructure and the core microstructure. So there it is not normally used.
Yeah. Another question is post force stress relieving necessary for low carbon steels, MS? Yeah.
Post forge?
Uh, Post forging stress relieving necessary for steels like MS, low carbon steel.
No, it is not at all required. Normally, for the grades where the alloying elements are on higher side or carbon is on the higher side, and when those are subjected for certain operation like straightening, then the stresses get incurred on the job. And to relieve the stresses or because of the heat treatment, and to relieve the stresses, the stress relieving is normally used. For the MS material, there normally no stresses are there, so it is not required.
Yeah. So for commercial heat treatment plant, how to select polymer quenchant at jobs and grades at jobs and grades keep on changing. So
Yeah,
commercial
actually,
aspect, yeah.
uh, normally in commercial heat treater shop, there are two quenching tanks are there. The one, if the polymer is used, the one tank is having the low concentration of the polymer, and the other tank is having the higher concentration of polymer. When it is having low concentration, it is near to the water quenching. When it is having the high concentration, it is near to the oil quenching. So based on the grade of the material, if it is N19 grade, suppose, then and the component is having say 2 inches section thickness, then it is quenched in the higher concentration polymer, maybe 14% to 16%. But if it is a plain 1045 grade steel, where there is no alloying element is there, that can be quenched in the low concentration polymer. So that flexibility has to be there by using the two different concentration tanks.
So another question is how to improve impact strength in 41 CR4. Required impact is 27 joules at
Mhm.
40 section for of part. It is 38 and length is 400 mm.
And what is the component he has mentioned?
Component material is 41 CR4.
Yeah. And what is the
Required
heat treatment?
impact,
Yes.
required impact is 27 joule.
Yeah. In quench and temper process, definitely 27 joule should not be a problem. What is the component? If it is in transfer direction or in the longitudinal direction, what is the component?
That he has not explained. If Mr.
Okay.
Sajane, if you could explain it, and if you could unmute yourself and explain quickly.
No, whom are you talking about? We cannot unmute themselves. Please, I will have to unmute him.
So, yeah,
So,
Sajane, SB Sajane,
Mr.
SB Sajane.
SB Sajane. Just a minute. Yeah, Mr. Sajane, you can now speak.
Yeah, hi, Sajane, Mr. Sajane, if you could ask question quickly. You have been unmuted. Okay, taking time. So we'll take another question. Can you explain
Okay.
banding types and?
Hello, sir. Hello. Hello,
Yeah,
sir.
yeah.
Quick.
Mr. Sajane is online.
Yeah, good evening, sir. Yeah, sir. I have on that one. This is a forged component, headed forged, and other rest of this is as rolled.
Okay.
And length is around the 400 mm.
It is upset job.
Yeah, offset forged.
Okay.
And its length is around 400 mm, and the section is around 38 mm.
Okay.
The required impact strength is, they are asking 27 joules at minus 40.
At minus 40. Okay.
Yeah, minus 40. But
Okay,
we are regular. Yes, sir.
Yeah, you can continue.
Sir, actually we have the open non-hot furnace, continuous furnace, 500 kg per hour,
Okay.
and we have done that 880 degree. Cooking
880 degree.
about 880 for 2 hours.
Okay.
Quenched in cold oil
Okay.
and tempered at 560
Mm-hmm.
for 2 hours.
And what is the hardness you got?
Hardness we are getting that 28 to 30.
That is the specification.
Yes, sir.
Okay. And what
Now
impact?
we are getting that at minus 40, around 24 to 26. This is near to the requirement.
Okay.
Could
What is
you
the
possible to improve that impact strength, sir?
Yeah. What is the time for tempering you are following right now?
2.5 hours, sir.
2.5 hours.
Exact soaking. Exact soaking is 2.5 hours.
Okay. So what are you say you are see the continuous furnace, you can slightly
Yes, sir.
reduce the rate of the pushing and increase the tempering time little bit. It can enhance the impact property.
At the same temperature or
Yeah, maybe you can slightly reduce the temperature by 5 degrees so that the hardness will not get dropped down much. And after tempering, you can cool it in the water.
hello.
After cooling the component, the tray can be
Okay.
quenched in the water, so that also enhances the impact property.
Okay, at the same tempering temperature, you have to
Mr.
quench in
Sajane,
water.
we cannot solve your complete problem right here in this technical talk. Please take this offline. Request you, please.
Yeah,
Okay,
he has said that you reduce your temperature by 5 degrees centigrade
Yeah.
and try it so that you will get that. Okay.
Slightly lengther, slow pushing that will increase the tempering time, and then you can cool in the water. After tempering, the tray has to be quenched in the water.
Yeah. So you can try this. Yeah. So next question is, can you explain more about grinding burns?
Yeah, grinding burn again, normally typically for the machine component like crankshaft, the grinding process is not under control. That the frequency for changing the grinding wheel or the coolant which is used for doing the grinding process, those are not properly monitored. Then there are chances that the temperature gets increased in some areas, and then the grinding burn occurs in that area. When you subject it for residual stress measurement by X-ray diffraction, you get some drop in residual compressive stress value over there, and that can affect the fatigue life of the component. So there are tests available to check those grinding burns, like chemical method is there, or there is a Barkhausen noise principle for checking the grinding burn. At our Bharat Forge company, we have got that instrument available, and in some testing like ARA also they are having that sort of equipment where that grinding burn test can be evaluated, and by basically controlling the process of grinding, that can be minimized.
Yeah. So there is another question. Can you explain banding types,
Yeah, normally
types and effect?
banding normally occurs at the steel mill stage during the rolling process, and during the steel making there is a process called as EMS, electromagnetic stirrer is there. If that process is uncontrolled, then there could be some banding for certain carbon manganese grade or some alloy grades where carbon and manganese are on higher side. So if the stirring takes place properly at the steel making, and their uniform stirrer is used and proper temperatures are monitored at the steel making, this problem can be monitored. Plus the temperature control during the steel making.
And what is the impact of that on the properties?
Normally for case carburizing grades like shafts or gears, if the bending is there, when you cut for the teeth over there, and because of the non-uniformity, hardness and microstructure of that bending process, you get the poor life of the component. So the one has to avoid bending as far as possible.
Yeah. Thank you, sir. There's another question, which is hollow star shaft forging. Which is the better, hot forging or cold forging for hollow shafts?
That depends upon the size of the component. If the size is big, normally it is hot forge only. If the size length of the component is small, and
Small,
then
big is around
cold forging also.
500 mm, maybe half a meter. So what could be
Okay,
the, yeah?
I think hot forging may be required for that.
Okay. Okay. So what is the ultrasonic test requirement of for sound forging?
Yeah, ultrasonic test normally when we say magnaflux test, it is for the surface defect assessment. When in the core some defects are there, we cannot test it by magnaflux. Those are to be tested by ultrasonically. So in the ultrasonic test, high frequency ultrasound rays, those are passed on the component, and at the core or maybe somewhere in the inside the component, some defect is there. That sound wave which is passed, that gets again rebound back, and then on the screen you can see the location and the height of that defect flaw, and based on that the ultrasonic expert, he can judge at what location the defect is there and what is the severity of the defect.
Yeah, what would be the reduction ratio required for sound shaft steel bar of say 150 mm?
Normally for automotive application, 5 to 1 reduction ratio is adequate. Sometimes up to 6 to 1 also people use, but 5 to 1 if it is there, it meets the all metallurgical and mechanical property requirement.
Yeah. Can you suggest 6-inch upset forging source in India? Flange dia is about above 240 mm. Do you
I
know
am not
of
got your
any?
question.
Yeah, do you know of any upset for forging source which can do 6 inches? This thing, for the
Often
flange.
I really don't know. I
Okay,
have to
okay.
search that.
Yeah. Major reasons of banding, yeah, of course, those are explained. Can you explain banding types? Of course, that is also explained. And yeah, that's also done. Just a moment. There are a few more. A lot of questions are here. Dimensional changes of solid and hollow components after heating and after quenching. What are the how are the dimensional changes of solid and hollow components after heating and after quenching? Of course, they
Again,
are very
it is a
different.
very vague question. That
Vague
depends
question.
upon what size of the component, how it is treated. Normally, to avoid the distortion, if it is a long slender job, it has to be properly supported during the heating, so that there is no sagging during heating process, as well as the furnace control has to be very good. One has to see that there is no direct impingement of the flame on the component, and the proper controls are required during heat treatment, as well as the quenching tank. Also, one has to have a regular check for the polymer or oil to see that they are not adulterated, or there is no impurities in those. The temperature normally maintained for those baths. So if all those cares are taken in time, normally distortion part can be avoided.
What is the impact on machinability and cutting tools because of isothermal forging and conventional forgings? That's the question. Machinability,
Isothermal,
impact on machinability
uh-huh.
because of isothermally cooled forging and normalized forging, or maybe
Okay,
in
okay. If it
conventional.
is, there is isothermally cooled process is there, then you get naturally very good structure. Like mostly it is machinable, and the machining is very good for those component. If it is a conventional forging is there and there is no proper cooling, then you get non-uniform structure and non-uniform hardness in the core. So those we face problem if you machine directly as it is. So if it is a properly cooled component, it always helps.
Yeah. So which grades are suitable for control cooling, and how to establish control cooling cycle for a given part? What
For
are the
control
critical?
cooling, there are
Yeah.
microalloy steel grades like vanadium microalloy steel 38 mm 5 or 42 Sierra 42 mm 3, or now non-vanadium grades are also there. That is 38 mm 5 without vanadium, or there are grades like C70 S6 for connecting rod. So there are varieties of latest micro steels are there in the market, which are being used very widely.
Yeah. And what are the critical process parameters for control cooling? If you
For
could.
control cooling, basically, the at the end of the forging, the temperature has to be properly controlled. Normally, it is say 1050 plus 30 minus 30. Then, when it is loaded in, there has to be a cooling tunnel over there. So that time in the cooling tunnel also has to be properly defined. And at the exit, the temperature should be lower than 550 to 600 degrees centigrade. So the entry temperature in the tunnel, holding time in the tunnel, and exit temperature in the tunnel, that has to be properly monitored. So to get the uniform microstructure and uniform hardness, uniform properties.
Yeah, thank you, sir. There are a lot of questions still unanswered. I mean, if you have time, I can take one or two more.
Mhm.
Yeah. So, how the Jomini value defined or selected according to the final power requirement? Example, gear core hardness. Take any range. What is the relationship?
Now, basically,
Jomini and
Jomini,
core hardness.
yeah, Jomini basically depends upon the chemist of the material. As I explained you, HMA 255, uh, based on the chemistry available, that is carbon percentage, manganese percentage, chromium percentage, nickel and vanadium. For every alloying element, there is a conversion factor is there, and there are certain guidelines available for particular DI value. What is the hardness achievable? Like grade wise, the DI values are known, and based on that DI value, we can get the desired heat treatment hardness and heat treatment properties. So that will vary based on the component and based on the grade of the material.
One last question. Can you please explain the inclusion testing? I think
Yeah,
this would be the
inclusion
last question. Yeah.
inclusion as per ASTM E45. Normally, inclusion ASTM E45 inclusions are tested. There are four types of inclusions: A, B, C, D. That's sulfide, alumina, silicate, and oxide. So there are acceptance norms are there. Those are from ASTM. Those are given, and normally for forging application or automotive application, too thin and 1.5 heavy. A type too thin 1.5 heavy, B type again too thin 1.5 heavy, C type too thin 1.5 heavy, and D type too thin 1.5 heavy. That is sulfide, alumina, silicate, and oxide. Those are controlled in that limit. Then the steel is considered as the clean steel. If your uh, any of the inclusion that is above these levels, then that is considered as the non-clean steel or some dirty steel. and during machining or post machining, you can have some problems, and maybe in machining that can machinability can be poor if the inclusions are on the higher side.
Thank you very much, sir. It was very
Sandeep,
heartening.
Sandeep, one
Yeah,
minute.
1 minute. Okay.
Abhay, I would like to know regarding this banding index, because we find a lot of confusion in that. People are having different versions on the banding index, and that properties are getting important nowadays. So can you just explain me so that where can I get the source of information?
Actually, for every customer has got his defined some binding norms, like they are like bias tempo earlier, or maybe for Tata Motors, they have given certain acceptable binding norms over there, or even for our certain export customers. So uh, for level 1 or level 2 up to level 3 it is acceptable, but level 4 if it is there and that binding is very heavy, then that is not acceptable. But up to level 3 it is acceptable. That means the binding is not very severe, and then that will not pose much problem in the post forging and post machining process. But the binding is very heavy, then because of the ferritic band, perlitic band, the hardness difference will be there, and that can pose a problem in the machining. You will not get the smooth surface, as well as the tool life will be poor. So that binding control is there, but that is not constant for every application. That gets changed based on the customer acceptance norm, and there are acceptance norm from certain customer. Based on that, we have to decide our acceptance standard for acceptance of the raw material.
They keep on talking about the banding index, so we couldn't really understand it. Banding index they are talking about.
So frankly, I also don't exactly know exactly what is that index, but from application to application and customer to customer, that changes.
Okay.
So if there is exactly some binding index norm is there, I will just go through that and I will let you know. But normally customer defines his own acceptance norm, and based on that the material is either accepted or rejected.
Okay, thank you.
Yes, sir. So thank you very much. It was very heartening to listen to you. Of course, really a lot of expertise is with you. So we would love to have one session on failure analysis, which you have already said that your core competency. So take some time out for us and oblige us for with one more lecture on failure analysis.
Okay.
So if you are ready, we can take it somewhere in June 3rd week or 4th week. So
Okay,
we'll be in touch with you. And thanks once again. And thanks to all the participants for nice participation. And also nice, people have waited till around 9 o'clock. So it's almost 9. So uh, it was nice to listen to listen to all the questions also. And thanks, you answered. Glad that you answered it well. Of course, you had a lot of experience in it, so you could do that. So thank you very much, sir, and thank you very much all the participants.
Sandeep, I have one small request for Abhay.
Yeah.
Why don't you become the member of our association, ASM?
Actually, I was member
This could
last
get
year.
benefit.
This year till I think August or October, my membership was there. I am a part of Forge and Foundry Technology Forum in Pune.
Okay.
So
No, but you can become our member, the ASM India chapter member.
Okay.
So you can get benefited by your experience and this thing. So
Yeah,
we will love to have that.
Yeah, Sabnis sir will oblige us because he's his close friend.
Oh,
So,
acha.
so that this thing is on Sabnis. So
Sabnis
Sabnis
hai
ji,
kya? Sabnis?
हाँ थे सबनीश जी थे.
yeah. We will discuss. Yeah, we'll discuss.
Okay, then Vivek can send him the papers in the
Yeah.
meantime.
Yes, I'll do that.
Thank you very much.
Thank you
Thank you
all.
very much, sir, for
It was nice seeing Mr. D.V. Shah also attending our meeting after such a long time.
yeah. It was very heartening to Thank you.
90 plus members.
Ah,
Yeah,
yes.
93. Yeah, we
Yeah,
clocked
good one.
93 this time.
Thank you, sir. Thank you very much.
Thank you.
Thank you,
We
sir.
acknowledge your presence and we need your blessing in most of lectures.
Okay, sir. Ending the session. Thank you all very much.
Thank you.
Okay.